Let's talk about gravitational potential energy now. So when we talk about gravitational potential energy, let's talk about having an object that is, let's see, let's have an object. This is our cliff. Let's say the cliff is 10 meters high, and let's say that we're talking about a rock. Okay, and let's say that the rock has a mass of 2 kilograms. At this point, at the top, the gravitational potential energy would be mgy, which is 2 times 9.8 times 10, which is 196 joules. Now, if the rock starts to fall off of the hill, and let's say it gets to about here, at the 5-meter mark. And we want to find out how much potential energy it has lost. Now we can obviously automatically see that it's going to have lost half of its gravitational potential energy. So at this point we know that it's going to have 98 joules of potential energy. But let's pretend for a moment that we don't know that and that we need to figure it out. So here we're going to say that we have mass times gravity times our height. And we have 2 times 9.8 times 10, which will give us 98 joules. Now, we could also ask the question, how much potential energy was lost between these two heights? So what was the change in the potential energy? So we could do this two ways. We could continue looking at it with the situation that we have here, and we could say, well, the change in potential energy is 196 minus 98. So we have the change in potential energy of 98 joules. Or we could change where our 0 point is. Our 0 meters right now is set down here at the ground, but it doesn't have to be. We could set our ending point here, this halfway point, to be 0 meters. And if we set that to be 0 meters, then this we can set to be 5 meters. So now, when I want to find out what is the change in potential energy here, I only have to look from here to here. And my potential energy at the top would be 2 times 9.8 times 5. Oops, that should be 5 there. Sorry about that. Which is 98 joules. So we get the same answer when we compare these two. The difference is that in our first situation, where 0 was the ground, we had to do 2 calculations and then subtract to get the final answer. Whereas if we change our 0 point to being the halfway, then we know that we've only gone 5 meters, and then that displacement, we only have to solve the problem once. So when you're doing gravitational potential energy problems, the thing to remember is that the 0 point is arbitrary. Well, this is a bit weird. I don't know what's going on with my pen right now. Okay, so we now have an idea about gravitational potential energy, elastic potential energy, and we talked about the fact that kinetic energy is the energy of motion. So now let's move on to conservation of energy. Conservation of energy is really a law. There's 2 different ways of stating it. One says that energy cannot be created or destroyed, it can only change form. We do this all the time when we turn on a light bulb. The energy starts as stored energy at the power plant, usually in coal. That energy is then converted to thermal energy as it's burned, and then it heats up the water. Water turns to steam, so there's some chemical energy going on there. Still lots of thermal energy. That steam then turns a turbine, so it changes to mechanical energy. And that mechanical energy changes to electromagnetic energy, which we then use in our light bulbs. The other way of saying it is that in a closed system, the total amount of mechanical energy present before a process starts must be the same as the total amount of energy at the end. In other words, the sum of our energies originally must be equal to the sum of our energies near the end. Because we're only talking about mechanical energy, you need to keep in mind that what we're really saying is that the potential energy original plus the kinetic energy original is equal to the final potential energy plus the final kinetic energy. This potential energy could be elastic, could be gravitational, or it could be both, but that's what you have to think about. So let's see if we can, let's take a look at conservation of energy, going back again for a minute to the mass and spring lab that we had just been looking at. Okay, so we're going to put the 100 grams back up here. Now, if we take a look at what's going on here with our third spring, we have a total amount of energy here. Most of it's potential gravitational. Let's not have any friction. We have a little bit of elastic potential energy, a little bit of thermal here because of the friction. But now I'm going to pull this down some. Our total energy in the system increases dramatically, but when I let go, watch what happens. The total energy doesn't change. What changes is how it's related within. We have a bit of kinetic energy, we have lots of potential energy, and we have elastic potential energy. This dark blue is the gravitational potential energy, so due to its position, that's why it's changing so much. And then the elastic potential energy due to its stretch or its compression, and kinetic energy, of course, due to the motion. So you can see that the total energy isn't changing even though everything else is. Now let's look at another example where we are looking at changes in energy as well. In this example, we have a skateboard park, and we have a skateboarder. We're going to start the skateboarder way up here at the top. And so she's going all the way back to the top and coming back down again. Now let's take a look at this in terms of a pie chart. We're going to have kinetic, gravitational potential energy, and again, let's not worry about thermal energy, but you can see that there's lots and lots of potential and then kinetic, and then they just switch back and forth. If we take a look at this in terms of a bar graph similar to what we did before, you can see that the total amount of energy stays the same, but what is changing is the potential and kinetic, and at a point halfway, they are going to have the same amount of potential and kinetic energy. So again, even though they're moving and things are going back and forth, the total amount of mechanical energy is not changing. So conservation of energy, we need to look at both the potential and the kinetic. We have to look at both the gravitational and elastic potential energy, as well as the energy of motion. So let's take a look at some conservation of energy examples here, and we'll put some numbers to them. So we have a hill, and on this hill we have a kid in a sled. Have to give her some arms here so they can hold on. Okay, so they're in the sled, and let's say that the sled is 5 meters tall. The question is, how fast is she going? At the bottom of the hill. Well, if we think about the conservation of energy, we have to look at the sum of the energies original. It needs to be equal to the sum of the energies final. Originally, we have potential energy that we need to think about. We have initial kinetic energy we have to think about. At the end, we have to think about the same. 2, there's nothing elastic going on here, so we don't have to think about elastic potential energy, just energy due to motion and due to its position. To begin with, because she's sitting at the top of the hill, she has no kinetic energy initially. And at the end, if we say that the bottom of the hill here is our 0 point, then she has no final potential energy either. So again, see, if I put the 0 point at a convenient spot, some of my terms go away. So my initial potential energy is mgy. That should be a final. My final kinetic energy is 1/2 mv squared. Notice that the masses cancel out, so it does not matter how much she weighs or what her mass is because they're on both sides, so they cancel out. So G is 9.8. Y is 5. I'm going to multiply through by the 2. So we have 9.8 times 10, which is 98. Is equal to v squared. So now we simply have to find out what the square root of 98 is, and it is 9.9. So her final speed when she gets to the bottom of the ramp is going to be 9.9 meters per second. Let's look at another one. Let's look at a pinball machine. When you start with a pinball machine, you start with a spring that you have to compress, and you have the ball in front of it, and this has been compressed from, say, here, its original length. So we could say that, for example, the compression of the spring was 0.2 meters. If the mass of the ball is 0.2 kilograms, how fast is it going when it is released? Again, we want the original potential energy plus the original kinetic energy to be equal to the final potential energy plus the final kinetic energy. Potential energy final is going to be 0 because it's not on the spring anymore. The initial kinetic energy is also going to be 0 because the ball is not moving. In this case, however, potential energy is not due to gravity. It's due to the elasticity of the spring. So 1/2 kx squared is going to be equal to 1/2 mv squared. I forgot to tell you that the spring constant for this spring is 1.3 newtons per meter. So the 1/2s go away. So 1.3 times 0.2 squared divided by 0.2 is equal to v squared. So that's really the same thing as 1.3 times 0.2, which is 0.26. That's equal to v squared, which means that v is equal to 0.51. So the speed of the ball after it comes off of the spring in the pinball machine is approximately 1/2 meter per second.